We really only need 3 columns. The picture becomes the X, flower is the Y, which is the class that we want to predict. And then as we just mentioned, let's use this fold A1 variable as our validation. If you wanted to do full 5-fold, you could pick fold A itself, the nominal version. But we'll just do a single holdout for sake of speed. Clicking OK brings up the secondary main model fitting dialog. And let's just go with the defaults here. It's fitting a LeanNet 5 model over 20 epochs and a learning rate of 0.001. Okay, the model's loading the dynamic libraries from Torch. Now it's loading all of the images in memory. Notice we've got 4,300 total, 80% of which are in the training set here. And now the model's training. We can see this LeanNet model is clipping along at a very nice pace and training the model quite rapidly. It's computing final predictions on all the images. It's done training. And here we go with results. We've got our first deep learning model in just a few minutes. Now the way the add-in works is you want to look at these training curves to verify that the model is either successfully converged or perhaps overfitting. There are 2 curves. The solid one corresponds to validation performance, which is arguably the more important of the 2. And then the dotted one is the training data, which will almost always be better. We're trying to minimize a negative log likelihood loss in this case. We can see here that the model is maybe doing okay, but not so great. Only 57% accuracy over the 5 classes. And by glancing through the results, we can see the model is getting somewhere. These ROC curves are definitely exhibiting some lift. But I'm wondering if we can perhaps do a little bit better. Only 57% accuracy is not that great. If we glance under these advanced options, we note that the LeanNet 5 model uses an image size of 28 by 28. That resolution is likely too small for these flower pictures. Let's use a more advanced architecture, the classic one known as ResNet 34. And increase our image size to 224, which is the size that was typically trained and used when forming the pre-trained weights behind many of the image models on the famous ImageNet dataset. Along with that, let's reduce our batch size to 64 because we have a rather small NVIDIA GPU that we'll look at in a moment. Let's not freeze any epochs, and drop our number of epochs to 10 and decrease our learning rate since we know we've got pre-trained weights already. And we'll just go with 0.001 now. And here we go. The initial part of the training is identical to before, where we're loading the dynamic libraries from Torch, as well as resizing and transferring all of the images into memory. Now here, because of the larger image sizes and more complex model, we do expect this one to run a little bit longer. We'll see just how long it takes as we go along. Now when a model's up and going, it's interesting to monitor your compute usage as it goes along. One good thing to check out is the task manager. If you click the Performance tab here on Windows, you can see this machine I'm running on has 2 different GPUs. One's an Intel UHD graphics card, and we also have an NVIDIA Quadro RTX 3000. It's the second card, the NVIDIA card, that's actually used for machine learning. Now, I'm not sure why, but my task manager, and this laptop's a few years old, it doesn't seem to track GPU compute time or compute activity at all, but it does show some memory usage here, 4 out of 6 gigabytes. So that's a little bit limiting, but there is another tool that we can use straight from the command line. And so if you just open a command prompt and issue the command NVIDIA-SMI right from a command prompt, and assuming that you have the CUDA libraries already installed on your machine, this command will work, and you can get an instant readout of the current GPU activity, memory usage, temperature, and other facts about what's happening. So you can see it right at the moment I pressed that Quadro card was at 77% compute, and we do have 5,900 gigabytes used out of 6,100. So the card's pretty much maxed out, and you can repeat this command as many times as you want. Now it's up to 90, and this is something good to monitor as the model is training, just to keep an eye on your compute. You may also hear my fan kicking on my laptop now, because this really is fairly intense operations, and it will generate some heat. If we glance back at our progress bar from jump, we see now we're into our second epoch out of 10. And oh boy, look at that. Our validation accuracy, at least here after 2 epochs, is already above 90%. So that's really good news here. It looks like indeed we're going to be able to really improve on that initial model that we fit. But we'll need to wait a little bit here and let it finish training. We're only on epoch 3. So it's a good time at this point to get a cup of tea or coffee. Our ResNet 34 model just finished. Total compute time is around 12 minutes. Not too bad for this setup on a laptop with over 4,000 images. And wow, look at the improvement in our validation accuracy. All the way up now to 91, 92% correct. That's great. Let's take a look now at these modeling results and see if we can drill down a little further. Jump provides a very rich set of interactive output in terms of various classifier performance measures. For example, confusion matrices and ROC curves. One plot I really like is this one called Prob Actual, where we can see the actual out-of-fold probabilities from our validation set, and we can interactively select the pictures that were misclassified. So I'm dragging a box here for all probabilities that are less than 0.5 from their true class. And let's now go back to our original table and take a look at these. Turns out we've got 99 selected. And if we do a subset, these are all the pictures that the model predicted incorrectly from the validation set. I find it informative to take a look at these, as you can kind of get an idea of maybe where the model is missing something, or just get a feel for how it makes mistakes. So for example, this first one is kind of a big field of daisies, not clear pictures of any one of them. You can see some of these other ones are somewhat unusual. This one here almost looks like a rose to me. And look at number 9 there. That really looks like a dandelion. So maybe some of these labels are actually incorrect. That can happen sometimes. Likewise, we can see some somewhat unusual pictures. That one just looks like a picture of the sky. I don't see how you could identify a flower from it. And here's one of a road. It's very faint, if anything. So you can, for images from the wild like this, sometimes you can really get some unusual performance. But it's always good to see where the model makes mistakes. And I think the jump interface makes it really easy for this kind of thing. All right, well, next steps for this modeling exercise would be to maybe try to fine-tune the model a little bit more, perhaps try a few other architectures, and then it's fairly easy to deploy models in Jump, either predicting new images right within Jump, or the models themselves are saved as .pt files to disk, which you can load into Python or other packages that recognize that format. For now, let's save our work so that we can pick up where we left off later. First, let's get rid of that poor fitting model from our analysis pane here. You can do that by unchecking the checkbox and then clicking the little red triangle, remove hidden models. Next, let's save a script of these settings to our data table. It's a nice property of jump tables where you can save scripts that you've previously run. And if you right click and look at edit, you can see what the JSL code behind the script looks like. You can see we're persisting each of the parameters that we set, and then the script we can run again later to reproduce our analysis. Finally, let's go ahead and just save our jump table, and everything will be buttoned together. I've selected this option to compress the table, which can help save a little bit of space, especially for large tables. Let's do a save as, and we'll call the data flowers 1. Overall, I find this Torch Deep Learning add-in to be very fun and convenient. It can save you a lot of time and mental energy. And even if you like to do deep learning in Python, it's often a great way just to get started, to quickly visually find out what's happening and fit a few models just to get a quick feel for the data before you really get serious in your coding. Either way, though, sometimes you can do everything right in Jump as well. In any case, I hope you're willing to give the add-in a try. You can find it on the Jump community page. Just download it. You need a copy of Jump Pro 18, and then just download the add-in and install it and try it on your own data. You might be surprised at what you find.